Okay, so now that we've motivated this idea of a partial derivative, that if I have a function of x and y, that there could be a rate of change, or I could see a change in f because I changed my input variable x, or I could find the rate of change parallel to the x-axis. And those are the two notations that we use. Or I could have changes in my function f of x and y if I have changes with respect to y. Okay. And I could have a function of three variables, x, y, and z, in which case I would actually have three options instead of two. I could have the partial of f with respect to x, or f sub x. I could have the partial of f with respect to y, or f subscript y. Or I could have a change in f with respect to z, or f sub z. So let's go ahead and take a look at a couple of examples, but as we do that, remember that if I'm finding the partial derivative with respect to x, then I am holding all other variables constant. The only variable that I'm interested in changing is the x variable. So let's go ahead and look at our first example here. So our first example is f of x and y is equal to x squared plus xy plus y squared minus 2x plus 4y plus 3. So let's go ahead and find the two partial derivatives. There are two partial derivatives because there are two variables. So I could have the partial of f with respect to x, or I could write that as f sub x. And so in this case, anything other than x is treated like a constant. So if I start with my first term, the partial derivative there would be 2x using the power rule. Looking at my second term, I treat that y as though it were a constant. So then I only take the derivative of the x, which is 1. My next term is y squared. Well, that's a constant in this case because we're interested in x, so that's plus 0. Minus derivative with respect to x. Here, for the minus 2x, it's just going to be a minus 2. Plus the 4y. The y is not the variable of interest. I'm not looking at letting y change, so that's a 0. And then plus 0 because my 3 is a constant. So what do I end up with? I end up with 2x plus y minus 2 as the partial derivative of f with respect to x. And I can do the same thing, or a similar thing, I guess I would say. Partial of f with respect to y. So in this case, now the variable I'm interested, the variable I'm allowing to change is the y variable. Okay, so in my first term, I have just x squared that I treat like a constant, so that's 0. Plus, again, y is the variable of interest, so the x I treat as though it were a constant, and I take the derivative of y. Partial of y with respect to y is 1. Plus, my next term is y squared. Take the partial with respect to y of that, and I get a 2y. Next term is a 2x. Take the partial with respect to y there, I get a 0. Plus partial with respect to y of 4y, I get a 4. Plus 0. And so what do I have here? I have an x plus a 2y plus 4. And that would be my partial derivative of f with respect to y. Now, in this particular example, I predominantly used the power rule. But as we go through, we'll see maybe a couple more examples where I'm going to use the chain rule, or maybe the product rule, or the quotient rule. So we do need to have command of all the various rules for differentiation. Okay, so let's go ahead and take a look at the next example. In this example, I've got z is equal to the natural log of x plus t squared. Now notice that this isn't actually given in a function form. It's more of an equation. And what we're after here is we want to find the first partials. So I need to think to myself, okay, is this a function? If it's a function, what are the independent variables? And so yes, it is a function. And my independent variables are x and t. So when I think about finding the partial derivatives of z, I will be taking the partial derivatives with respect to x and with respect to t. So let's go ahead and do that. So I want the partial of z with respect to x. It doesn't matter which order we do them in. So I have my function being the logarithm, so it's going to be 1 over the argument of the logarithm, so 1 over x plus t squared. Then I take the partial derivative with respect inside the argument. So the partial with respect to x of x is 1. The partial with respect to x of t squared, that's a separate variable. It's a separate independent variable, and it's not the one I'm focusing on, so that becomes a 0. So I end up with 1 over x plus t squared as my first partial derivative there. I can do the partial derivative with respect to t, and because it's still the logarithm function and the t is embedded in that argument, I'm still going to have this 1 over the quantity x plus t squared. But when I go to take the partial derivative of the argument, this is where things are a little different. This time, my variable of interest that I'm focusing on, that I'm allowing to change, is the t variable. So that means that this x I treat like a constant, so the partial of x with respect to t is 0, plus, and then I take the partial with respect to t of this t squared, so that gives me a 2t. So my partial of z with respect to t is going to be 2t over x plus t squared. And you'll notice that every time something, when we take one of these partial derivatives, and it happens to be one of the other variables, I'm explicitly writing a 0 to call attention to the fact that we did pay attention to that, and that the partial derivative of this t squared with respect to x was in fact 0. Okay, so let's go ahead and look at another example. And this one, so if you'll recall from Calc 1 and the fundamental theorem of calculus, if we have a function, we'll call it f of x, and it's defined as the integral from some constant to a variable x, and let's say this is cosine of t squared dt, okay? And we were asked we could find, using the fundamental theorem of calculus, we could find f prime of x. Now, just so you know, that integral from a to x of cosine t squared dt, that is not integrable. In other words, it doesn't have an antiderivative, so we cannot find that antiderivative and then evaluate between x and a. That's not a possibility. But the fundamental theorem of calculus provides for us a means by which we can actually find the derivative of that thing, even though we can't actually integrate it. And so hopefully you recall that when we had a function defined with an integral, provided the independent variable was in the upper limit of integration, we simply took the integrand and replaced the dummy variable, in this case the t. We replaced the t with an x. So the derivative of this function defined using an integral is in fact just cosine of x squared. So we can do the same thing, and that's what I want to do next. Is we have a function of x and y. And so our function of x and y is an integral from y to x of cosine of e to the t dt. Now, I made that kind of ugly because I didn't want you to be tempted to try and integrate that thing. It can't be done. The antiderivative does not exist. Okay? So, but here's what I want us to do. I want us to find the first partials. Okay, so that means that I am looking for the partial of f with respect to x. So what I'm going to do is I'm going to take the partial with respect to x of the integral from y to x of cosine of e to the t dt. Now, since this is a partial derivative with respect to x, we treat y as though it were a constant. So we can do this in much the same way as I talked through this first example. So basically I take my integrand and I replace t with the variable x that's in this upper limit. So this would be cosine of e to the x. And I can do a similar thing with the partial of f with respect to y. Now I have to work a little bit harder on this one. So we're doing the partial with respect to y of y to x, cosine of e to the t dt. Remember that this worked provided that this lower limit was a constant. Well, in this case, I have y as my lower limit, and that's the variable I'm interested in. X is the variable I'm going to be treating as though it were a constant. So what I want to do is basically reverse the limits of integration. So we're going to have to put a negative in front of our integral. Then we'll have x as our lower limit, y as our upper limit, and we'll have cosine of e to the t dt. And now in this case, since it's a partial derivative with respect to y, I treat x as though it were a constant. And now that constant is down at my lower limit, so I can go ahead and use that fundamental theorem of calculus. And this time, don't forget our negative because we had to flip the limits of integration. And so now I replace t with y, and so I'll have cosine of e to the y would be that partial derivative.